Thank you so much for tuning into my presentation on calcium-ion batteries. Let's really quickly go over their history. Calcium-ion batteries were initially theorized in the 1960s when scientists were looking for viable alternatives to lithium-ion batteries. Calcium came out as a primary competitor due to it being way more abundant, going from lithium's about 20 parts per million to calcium's 45,000. It was also exceedingly cheaper, reaching $40 to $50 per kilowatt hour, and also its higher boiling point meant it also was able to work similarly at higher temperatures. However, this would also lead to great detriment due to researchers at the time not being able to figure out how to work around the higher operating temperature. Let's really quick go over how a battery works. The quickest way to describe it is ions move from one end of a battery to the other, either releasing or collecting electrons in the process. The electrons that are released then go into a circuit that can do work. So here we have a couple schematics. If you look at A here, we have a calcium air battery, and it's the way that it moves. So we also have a calcium sulfur battery, along with a general schematic for a calcium ion battery. In the bottom, we also have just a general battery diagram. One thing you'll notice on the calcium ion battery schematic to the left is that there is a passive layer there, which we will talk about in a little bit. Now, research has been done on many different types of calcium ion batteries with different materials, all to varying degrees of success, some of which we'll talk about in the later parts of this presentation. But the one that we'll be going over is primarily made of a calcium anode, of course, with a graphite cathode, and then an electrolyte made of a mixture of a couple different metals. We can see here the cathode and anode reaction for this specific battery, where calcium reacts with chloride to release electrons, splitting into calcium and chlorine gas. And then to charge it again, we add electrons to calcium in order to balance it out. Let's also really quickly go over some math. The two main things that we use in order to measure battery, how good a battery is, we'll say, is capacity retention. So this is like it's how long a battery can last, almost. This capacity retention is basically how much charge a battery will continue to hold after being charged and discharged over a period of time. So in this case, we have the amount of reactant left, depending on the battery. So this time it would be calcium, is equivalent to the coulombic efficiency of the battery to the nth power, where n is the amount of cycles of charging and discharging that battery has undergone. So this is the reason why your iPhone 7 doesn't work without being plugged in anymore, because you've charged and discharged it so many times by using it that the amount of lithium left in the battery has been more or less used up. Another metric we use to measure batteries is specific capacity. This basically determines how much charge can be held per unit of mass in the battery. You want to maximize this so that you can fit as much power as you can inside the smallest battery. But how does this measure up to a commercial grade lithium-ion battery? A calcium-ion battery's current energy density reaches about 108 watt-hours per kilogram with a power density of 131 watts per kilogram. This means that if you put in 131 watts into a 1 kilogram battery, then over an hour you will receive back about 108 watts. By comparison, a commercial grade LFP or lithium ion phosphate battery, reaches between 90 to 160 watt-hours per kilogram, depending on its power density. As you can see, this is a little bit higher on average, but again, remember that calcium is way more abundant than lithium. So what this means is that calcium is going to be way cheaper in the future compared to the manufacturing of a lithium battery. Another thing is that calcium is also divalent. If you see here at the table at the bottom, you'll see a column labeled charge where calcium has 2+, meanwhile lithium has 1+. This means that calcium has 2 valence electrons compared to lithium's 1, which means that there are double the amount of electrons that calcium can donate to a circuit to do useful work. So this also means that calcium technically has a higher energy density than lithium. Once more research is done and calcium batteries are optimized, it is more likely that they will have a higher energy density than lithium. Calcium ion batteries and lithium ion batteries have similar round-trip efficiency. Calcium has a little bit lower than it, but what round-trip efficiency is how much energy is lost per charge and discharge. So if we remember, we were talking about charge retention. Round-trip efficiency is basically how much of that we lose each time we charge and discharge our battery. So here we come to the cons. A calcium ion battery, unfortunately, has a very low cycle life compared to a lithium ion battery. While lithium ion batteries can theoretically go up to 3,000 cycles for some of the higher end electric vehicles, the highest recorded calcium ion battery was only able to go for about 1,000 cycles. This lowered cycle life means that you will have to be replacing calcium ion batteries much more frequently than a lithium ion battery. In addition, the coulombic efficiency also needs work. Calcium ion batteries, unfortunately, have the issue of calcium metal being a little bit too reactive. So because of that, a calcium metal anode, because of its reaction, eventually builds up a small layer of byproducts called a passive layer. This renders the metal chemically inert and unable to produce more electricity and release more electrons back into the circuit that it's a part of. Lithium does not really have this issue, thus increasing its cycle life and retaining coulombic efficiency. So what does calcium have over everything else? Well, first of all, calcium is extremely abundant. Again, you've heard me say this before, calcium takes up about 5% of Earth's crust with its 45,000 parts per million, compared to lithium's 18 parts per million, or about 6.5 to the times 10 to the negative 4th power percent of the Earth's crust. So again, that means that calcium batteries are very cheap to manufacture. Another thing is that because of calcium's divalence, that being it has 2 electrons to donate during its electrochemical reaction, means that it electrolyzes very easily. This also goes hand in hand with its low redox potential. So what redox potential is essentially how likely it is for a metal to reoxidize after releasing its electrons. So obviously there's not just one calcium molecule releasing its electrons into a battery, right? So there's a chance sometimes that a calcium ion will capture another calcium ion's electrons, therefore reoxidizing itself and bringing itself back to a neutral state prior to the electrochemical reaction completing, basically it making it from the anode to the cathode, right? So this is usually represented by a number, and calcium notably has a redox potential number of negative 0.84. This is compared to lithium's negative 3.07. So what this means is that lithium is actually slightly less likely to oxidize compared to calcium, but this performance hit outweighs all of its other advantages. Again, calcium, so another thing, calcium being divalent, again means that it has a higher energy density than lithium because it has double the electrons to give. So that means that, or well, it doesn't necessarily mean double the electricity, but when optimized, that should mean that it eventually will release more energy than lithium. And by optimized, I mean like its battery design and such, once we figure out all of its other problems. Calcium, again, also as an anode, is notably dendrite-free. Dendrites are small byproducts that are left on an anode that can impede the electrolysis of its ions when it comes in, or when it comes in from the cathode, right? So excessive dendrites can eventually lead to rendering the battery chemically inert. And they are difficult to remove because they are mostly microscopic or smaller than that. So dendrites are usually a major problem for batteries, but calcium ion batteries notably do not come across that issue. Now, of course, this battery isn't on the market, so here are a couple reasons why. Firstly, calcium has the tendency to develop a passive layer. So every so often, again, a calcium anode, essentially every cycle, it will develop a very thin layer of nanoparticles that, once built up enough, will render the battery chemically inert. So what this means is that now ions will no longer be drawn to the anode, and thus will no longer be willing to donate their electrons to the circuit for the cause. This is the biggest hurdle when it comes to calcium ion batteries, because it severely limits their efficiency and it severely limits their cycle life, which are the two things that lithium-ion batteries currently have over calcium-ion batteries. Once you fix that passive layer issue, then you get the chance to fully reap the rewards of a calcium-ion battery. Another thing is that, remember back when I was giving that history lesson, one of the reasons that calcium-ion batteries were tabled as a possible option for energy storage was that they operate very well at high temperatures. But this also means that they are the most efficient at high temperatures. So once you're near about the boiling point of water, 100 degrees Celsius, that's when calcium ions really kick into high gear. Unfortunately, what electronics are you aware of that like to operate at the boiling point of water? Right, very few. So because of this, it's a little bit difficult to get the proper partner for calcium. So that's why we've tried things such as chloride, such as oxygen, and other different media, other different particles, to try and bring the operational temperature of calcium ion batteries to a more stable, such as room temperature, or maybe a little bit, up or down from there. Calcium ion batteries also suffer from structure instability. So what this means is that the cathode has to be designed very specifically in order to make sure that the passive layer does not build up too quickly, nor that other byproducts will be formed from the electrochemical reaction, right? So because calcium is a divalent metal, that means that it has a lot of electrons to give. That means that it reacts with a lot of things, especially since it's an ion, and ionic compounds are kind of everywhere, especially calcium-based ones. You have calcium carbonate, you have somehow they're all evading me right now. I apologize. But this structure instability can lead to byproducts which are not what you want inside a battery. In addition, with this reactivity comes the issue of the electrolyte medium. So, of course, you have your anode and your cathode, but the electrolyte in the center that the calcium ions pass through have to be specifically something that will not react with the calcium ion. Some of them have a chance to combust into flames or even explode, which obviously poses a very massive safety risk for a calcium ion battery. You remember the lithium ion battery scandals from Samsung, right? With them exploding in your pocket. We don't want a repeat of that. So researchers have been trying to figure out which electrolytes are the best for calcium ion batteries without rendering them explosive. So who's investing into all of this stuff? Well, a lot of the journals that I found were actually all mostly sponsored by Chinese universities. Stuff like the University of Hong Kong of Science and Technology, or the Hong Kong University of Science and Technology, apologies, were some of the main investors in calcium ion battery technology. A lot of the journals that I read were by Chinese authors, and they had some of the more recent breakthroughs, including one from March of this year, in fact. Another major player in calcium ion battery research is Ambri LLC. Ambri is a proprietor in liquid electrolyte calcium ion battery technology, with one of their major investors, in fact, actually being Bill Gates himself. He's been trying to invest in green energy, and one of the main things about green energy is storage, and calcium ion batteries have been a great boon in that. So why don't you see this on the shelves everywhere? Well, again, we still have not solved the issue of passive layer buildup on the calcium anode of the battery. You've heard my spiel plenty of times. And another thing is that manufacturing at scale still requires more research, right? Since we haven't solved the passive layer issue, along with calcium ion batteries, a host of other issues, it is still difficult to manufacture at scale, as there has not been much research put into it, because the battery still really isn't ready for commercial use yet. So what are we doing to fix these things? In order to fix the passive layer, one of the things that we have been trying to do is make buffer layers. So these buffer layers made of graphite sheets will help limit the buildup of byproducts in calcium ion batteries, and sometimes they're also made of stainless steel. Sorry. In order to limit the buildup of byproducts on the anode of calcium ion batteries, this means that the battery will last a little bit longer, along with having a little bit better cycle efficiency. Another thing is those electrolyte materials. One of the things we have tried is using a water in salt electrolyte, which dilutes the solution a little bit, but means that it is less volatile. Additionally, we have tried water in gel instead of salt, specifically for wearable technology. So what water in gel does is it is a little bit more inert than salt, which means that it reacts a little bit less, it's a little bit safer, and thus more likely to get approved to be on your wrist or anywhere else on your body. So looking towards the future, could calcium ion batteries work? Oh yeah, they can. Again, calcium is kind of everywhere, and it being so cheap means that they can be super widespread. Once you solve all of their issues, they could even potentially replace lithium-ion batteries in most commercial electronics until you need ones that last a really, really, really long time, or you're looking for a lap of luxury stuff. Again, you have your wearable technology due to water in gel electrolytes. Another thing is gel is a slightly better heat conductor than salt is, so it will be able to not overheat as easily compared to other batteries. Because calcium ion batteries have a chance to be very easily mass producible, they could also be used very easily in grid storage, where you need a lot of batteries, a lot of big batteries, in a lot of time, or for a long time. In addition, it could also be used in EVs, because they line up, their lifetime lines up with about the same amount of time as a car would, because once you fix, again, that passive layer issue, you no longer have the issue of dendrites in lithium-ion batteries, which is the main reason why they are not as great in EVs or grid storage as calcium ion batteries would be, just because they wouldn't have as much longevity. In conclusion, calcium batteries are very promising in terms of their cost and their energy density, along with being very abundant, which would give them a chance to become very widespread across the entire world, as we make an attempt to move from fossil fuels towards green energy, and need to find a place to store all that power. However, they still have the key weaknesses of that passive layer buildup, and other byproducts coming from calcium being extremely reactive. So once those issues are solved, well, the sky's kind of the limit. Thank you so much for watching.